Monday's class was about addressing goofs from the previous class, from last Wednesday's class. So today, I'm at least addressing a goof from Monday's class and then continuing on. So an example I did at the end of last time was this non-homogeneous wave equation where the right-hand side is a function of, normally a function of x and t, but in this case it's really just a function of only x and these initial conditions. And I wanted to separate it, or to be able to handle this easily by integration. And I concluded at the end that if it depends on t, you can do this, whereas if it depends on x, you cannot. That is wrong. You can handle this the easy way if it depends only on x. You just have to be a little more careful about it. So procedure is not exactly the same. So like before, we break a solution down into u into v plus w. W satisfies, I'll write out both. Okay, so, and v is a function of only x. Therefore, both time derivatives, vt and vtt, will be 0. So which problems do these satisfy? For v, the t part is gone. So we have minus 9 vxx equals 2 sinh x. And then, for the initial conditions, the key is don't fill them in right away, at least not this first one. You won't know what this is until you actually solve this equation by integration. Now, dv dt of x0, that's still 0, because your solution is going to be only a function of x. So its time derivative is going to be 0 everywhere, not just at t equals 0. So we have an incompletely specified problem. And then what about w? Well, w satisfies the regular homogeneous wave equation. Okay. And then, what about the initial conditions? Again, you have to be a little more careful. So w of x0 is going to be the initial data from the original problem, x, subtracting off your v of x. Yeah. So
0 or just v of x?
Well, really v of x, because v is a function of only x. So in fact, these don't even need to be here. Yeah. So, and then dw dt of x0 is the same as for u, sine x. So the idea is you go ahead and solve this, come up with the simplest solution possible. Like, don't bother having your constants of integration. So really the solution is not unique, but you just need a solution. And whatever you get, just subtract it off here. And then use the homogeneous wave equation formula. So now we go ahead and solve. So we have vxx, really it's v double prime, because it depends on only x, is minus 2/9 sinh x. So, as you know from last time, the integral of sinh is cosh, but then we integrate again. The integral of cosh is sinh. So it turns out that, okay, so v, the constants is going to sit there. So v prime is minus 2/9 cosh, and v will be minus 2/9 sinh. And like I said, there's no need to add on plus c's because you just need to satisfy, you just need any function that satisfies this differential equation. So that takes care of v. And this is part of a solution that's in the notes for this problem carried out the other way using that god-awful solution formula where you integrate over a characteristic triangle. Now, we know what to solve for w. So w of x0 is going to be x plus 2/9 sinh x, because we're subtracting off our v. So now we can apply the elaborate solution formula for a homogeneous wave equation, and we get w of xt is this function evaluated at x plus 3t and x minus 3t, because, well, from the original PDE, c is equal to 3 now. So we have x plus 3t plus 2/9 sinh x plus 3t, and then plus x minus 3t plus 2/9 sinh x minus 3t. Okay, so that takes care of this part of the solution formula. And then you have plus 1 over 2 times 3 integral from x minus 3t to x plus 3t of dw dt at x0. So that's sine s ds. Okay, so we have, okay, so here's our solution v, that's really v of x. And then we have our w of xt right here. And if that integral can be worked out and so forth, then there are certain simplifications, like this 3t cancels with this minus 3t, and so on. But if you slap these solutions together, you have a solution that's in the notes for when this example was done using the original solution formula using characteristic triangle. So, but here, there's no need to do a double integral. So carrying it out this way, so bottom line is, if your f of xt depends on only x or only t, there is an easier way out. It's just that when it's only a function of t, you're solving a problem like vtt equals something, and you can make sure that it satisfies 0 initial conditions. When it's depending on only x, you can't do it that way, but you can just go ahead and solve it the simplest way possible and subtract it off for your initial condition for the other problem, and use a homogeneous solution formula, and you're done. So, so for any homework problems with a non-homogeneous wave equation, if it depends on only x or only t, don't use that characteristic triangle integral. There's a less painful way to do it. Okay, so any questions about how this one was solved? All right. So now, what we've done so far, because like all the problems we've been doing so far, this is a Cauchy problem, meaning that the PD is defined on the entire real number line. So now, as we finish finally chapter 4, which I definitely spent more time on than I planned, and we move into chapter 5, we're now going to start solving similar kinds of PDE, but on a bounded domain. So we not only have initial conditions like these here, we're also going to have boundary conditions. But we have a nice solution procedure for these cases known as separation of variables. Okay, so that's what we're going to spend the rest of the day on. And then this is our last class before spring break, of course. When you all come back from spring break, Dr. Tian will be substituting that first week afterwards. She'll be continuing with chapter 5, and then I'll come back and finish it off. Okay. And today we will look at separation of variables for the heat equation. Dr. Tian will cover this from a wave equation right after spring break, but the procedure is quite similar. Okay. Now, so our initial boundary value problem. So I'm just going to focus on this IBVP for today, so you get an idea what to do. So, by the way, in these notes for this lecture, I've picked out 2 problems from Chapter 5 that are related to this material. There will be more Chapter 5 problems. They just come from the later sections, and I'll pick those out later. So don't think you're getting off easy with the Chapter 5 homework. There is more to come. So we have a heat equation with a constant coefficient K. And then we have, and we're working on a bounded interval. So x is only between 0 and L, or whatever L is. Okay, and then we have our initial condition. U of x0 is f(x). And then our boundary conditions, we're going to require that the solution is equal to 0 on the boundary. Okay, for all time. And these are known as Dirichlet boundary conditions that specify the value of a solution at the boundary, as opposed to, for instance, Neumann conditions specify like the first derivative at the boundary. Okay. Now, the form of our solution that we will impose is some linear combination. There's some constants v sub n times certain solutions that I'll label as u sub n. And these are chosen so as to satisfy the PDE and the boundary conditions. So each one of them satisfies those. And then the constants b sub n are determined after that by the initial conditions, or at least in this case we just have one initial condition. Okay. So we're going to do this one step at a time. We're going to take care of these things first, and then handle getting these constants. Now, this works because, and actually this BC means because, not boundary conditions, so sorry for the ambiguity there. This is possible because the PDE is linear. That if you have solutions to a linear PDE, any linear combination of them is also a solution. You got to make sure they satisfy the same boundary conditions too. Okay, so we're just taking advantage of that convenience. Okay.
Is that sorry, after your B of n, is it a little u or big U of n?
Oh, actually, this is in the notes. This is a big U. So
Does it matter?
Actually, no, because I don't have a little un in the notes. So whatever you want to do.
Okay.
Okay. Yeah. So there won't be any ambiguity.
Okay.
Okay. Okay. So now what we're going to do is we're going to assume. Now notice I have n, little n, going from 1 to infinity. Now, depending on the kind of PDE, it may go from 0 to infinity. It's just a notational convenience. But for this problem, 1 to infinity makes the most sense. So for each n, we're going to assume that each of these solutions, u sub n, that we're looking for, has this form. So it is a product of a function of x only times a function of t only. So this is what is meant by separation of variables. What we're actually going to do is we're going to take a PDE that has 2 independent variables, x and t, and solve it by breaking it down into, bless you, 2 ODEs, one for each of those variables. And this is possible because the PDE has constant coefficients. So generally, it's only this approach, separation of variables, is only allowed in that situation. There are certain special cases with variable coefficients where you may be able to use the procedure also, but generally not. Okay. Of course, my whole research is on variable coefficient problems, but whatever. So, okay. And the other certain irony that to anyone I describe a research program to, how I grumble about the fact that in classes you only see nice constant coefficient problems, and here I am teaching that very thing.
And you also have discontinuous coefficients.
That's true, I do. Yeah. So,
Very fast.
But you have to learn the constant coefficients before you do
exactly, that's the problem. The
And
real
the
problem is not what I'm
discontinuous
doing. The problem is there's no room in the curriculum for anything else. So, yeah.
Like
Okay.
number theory. Like more of that.
That's a separate issue. Yeah.
Well, but you said there's no room for anything else, so I'm just
Okay, yeah, that's a bit.
fighting my opinion there.
Okay, well, yeah, that's it. There's a lot of things that we'd like to make room for.
See.
Number theory should be high up on the list.
You said shouldn't be?
Anyhow,
No, it shouldn't be on the list.
Oh, I thought you said it
Altogether.
shouldn't be. What, excuse me?
It shouldn't be on the list altogether.
well, actually, now we have 3 people in this room who either have worked or will work on discontinuous coefficients. So, yeah, even harder category problem, as you well know. Okay, now, so what we can do is take this form and substitute it into the PDE. So UTT equals K UXX. If we go ahead and plug this in, for U, what we're going to get is, well, dudt only differentiates the t function. So we get xt prime. And on the right side we have k. And then only the x part gets differentiated over here. So we have x double prime t. So then what we do is rearrange this. Really, we divide both sides by xt, and we're just making the assumption here that they're non-zero. And what happens is, after simplifying, like the x's cancel here and the t's cancel here, you get t prime, and I'm going to move the k down here. So t prime over kt. It doesn't really matter where I put it, it's just what it says in my notes. So is x double prime over x. Okay. Now, the key to the success of separation of variables is this nice little fact, that the left side is a function of only t. The right side is a function of only x. Now, the only way that an expression that depends on t can equal an expression that depends only on x, for whatever values of x and t, is for both of these expressions to be equal to a constant. So I'm going to equate these to a constant, and the constant will be minus lambda. Now the minus seems kind of strange, but you'll see in a bit why I choose that. And this is called a separation constant, or maybe constant separation, whatever. Okay, because now what you can do is, if I consider this equal to minus lambda, and then this equal to minus lambda, so 2 separate equations, I now get 2 ODEs, one for x, or for capital X, and one for capital T. So I have, okay, I should have subscripts of n through here, but anyway, xn double prime plus lambda xn is 0. And then I have tn prime plus k lambda tn equals 0. So this is how separation of variables works. I've separated a PDE into 2 ODEs. All right. Now, we're not dealing with the initial conditions for now. We've set that aside. But we do have to worry about the boundary conditions. But they're going to apply only to x. So I have xn of 0 is 0, and xn of L is 0. The t part does not have boundary conditions because it depends on t. So we just have only these to deal with. Okay. Now, there are three cases to consider about this separation constant, this minus lambda. Lambda itself can be either, of course, positive, negative, or 0. And what we'd like to do is try to figure out, can it really be any of those things, or are there certain cases that can be ruled out? Because that determines how we solve these ODEs. Because when you solve second order ODEs in like Math 285 or whatever your first DE course was, sometimes your solution had sines or cosines. Sometimes it had exponentials. Sometimes it had polynomials. So the question is, which is it? We'd like to be able to stick with one kind of solution if we can. And fortunately, in this case, we can. Okay. So here are the possibilities. Let's suppose that lambda equals 0. Well, then our second order ODE reduces to xn double prime is 0. And we also have the boundary conditions. But when a function's second derivative is 0, what do we know about the function itself? What kind of function has a second derivative of 0? What?
Sine and cosine.
X plus c.
Yeah,
Linear
linear function.
Oh, 0. Sorry.
Yeah. Okay. So we have xn is equal to some constant an times x plus bn. So it has that form. However, don't forget the boundary conditions. So once we enforce the boundary conditions, what linear function will satisfy them? Well,
So
Think-
then bn will be 0.
yeah. Yeah. Only 0. Yeah, because, well, first of all, a line is completely determined by 2 points. 2 of the points are 0.
So the xn equals 0.
Yeah. So, but that's no good for us. So this case is out because we need non-zero solutions. Otherwise, 0 would be the only solution of a PDE, and we could not possibly satisfy any initial condition except 0. Okay, so lambda at least has to be non-zero. What if lambda is negative? So in that case, we have so xn double prime plus lambda xn is equal to 0. But then, actually, if I write it this way, xn double prime is equal to minus lambda xn. But this is now positive quantity. And when that happens, you actually get exponential solutions that are exponential. So your general solution is of this form. It's a constant e to the square root of minus lambda x plus another constant e to the minus square root of minus lambda x. Because the square root is fine, because minus lambda is positive, so you're not having any imaginary numbers here. Okay, but then you have the boundary conditions. You plug in x equals 0, your exponentials become 1, so you get an plus bn 0. And then for the other boundary condition, we have an e to the square root of minus lambda L plus bn e to the minus square root of minus lambda L is 0. So what we have is a system of 2 linear equations in 2 unknowns, an and bn. But if you have a system of linear equations that is homogeneous, that has a unique solution, what is the solution? 0. And you can go through the Gaussian elimination if you want. I won't. But these 2 linear equations are literally independent. So homogeneous system, unique solution. only has a trivial solution. So again, we have xn is 0. We can't have that, so this case is out. And that's actually why I went with minus lambda instead of lambda. So we must have lambda being positive. So xn double prime plus lambda xn equals 0 tells us that the general solution is a constant times cosine squared of lambda x plus another constant bn sine squared of lambda x. Okay, so presumably this one is viable, but we need to make sure by checking the boundary conditions. Now I should point out, here we're assuming Dirichlet boundary conditions. If we have Neumann boundary conditions or mixed boundary conditions, we're still going to have a general solution like this. Some linear combination of cosine and sine. So far, this procedure is, whereas if we have other boundary conditions, these two cases would again be out. Except possibly the lambda equals 0 case. Only now do things start to get a little slightly different based on the boundary conditions. But I'll discuss other boundary conditions when we get to the end. Okay, yes?
I have a question. I think on check 517, they didn't have square root of lambda, we just dealt with lambda. Didn't we use like lambda squared?
Yeah, but I'm conforming to this textbook.
That's fine. Like, what's the difference? Like, did they set this over here equal to lambda squared or something? Like how?
Yeah, that's way back over there we did it because actually they went from the same cases. And then
I remember that. There's a chart. There's a chart.
Yes, and the idea is because you find by concluding, oh, this has to be positive.
Yeah.
So we write it
Like
as something squared
right.
to enforce positivity.
Because I didn't remember the square root.
Yeah, and the thing is, really what it did in the 517 book is better because they only get square roots all over the place. So I don't think
those are a pain in the butt to write.
I know, but we'll get around to it soon enough. But
okay.
yeah. Now, on the other hand, there is a good reason for doing it this way, because this is supposed to be an eigenvalue problem. Lambda represents an eigenvalue, and the only way that's true is if you leave it like this. Otherwise, you're saying lambda squared is the eigenvalue. Why are you twitching?
Because you know I don't like anything that has to do with linear crap.
Okay. You know, you did like that stuff at one time.
I don't need any more.
What?
I don't need any more.
Well, not my fault. So. Alright, so try not to come all unglued. So. Okay.
Sure.
Alright. Now, okay, so let's enforce the boundary conditions. So xn of 0, well, cosine of 0 is 1. Sine of 0 is 0. So we just get an, and that has to be 0. So that's nice because it gets rid of this term. And then the other boundary condition, xn of L, so that's just going to be bn sine square root of lambda L. And I want to emphasize the L is not under the square root. That has to be 0. Now, to figure out what lambda is, we use this boundary condition and what we know about sine. When is sine equal to 0? At what points?
0.
0.
And
pi.
and
pi.
Or multiples of pi.
yes, integer multiples of pi. So what that means is this expression that's being plugged into sine, square root of lambda L, must be some integer multiple of pi. And I'll go ahead and use n because I've been using n as an index anyway. So now I can solve for lambda. So lambda is equal to n pi over L squared. And therefore, my solution, xn of x, is, now, I'm just going to, for convenience, we know this is not 0. I'm just going to set this equal 1. I mean, we'll bring this back later when we deal with initial conditions. I just don't want it part of my fundamental solutions now. So we'll just define xn of x to be sine, because we can normalize this any way we want. And this is n it's non-zero for all positive integers n. It's 0 at selected points, but actually it's only 0 at the boundaries. Well, and certain points in between. But the point is, the function itself is non-zero. So this is a usable solution. And lambda is an eigenvalue of the differential operator minus x double prime. Okay, so it's an eigenvalue of that problem, and the solution that satisfies this equation is called an eigenfunction. And we will be studying these in much greater depth later on. Okay, so Corey just has to deal with it. All right. So now we've solved for one of our solutions. We have xn of x, and we know what lambda is. So now we can go and solve for the other part, Tn of t. So I should mention, it's a sign because of a boundary conditions. The solution is 0 on the boundaries. If it was a derivative being 0 on the boundary, one second, we would have cosines, because the boundary conditions would naturally enforce that. Yes?
So for the boundary of L, the a n is 0, so that went away. Oh, well, below that. So the xn of L.
Yeah.
So we know. So the first term goes away completely because a of n is 0.
Yeah. So because of this, we took advantage of this knowledge right away.
Oh, I see. Okay.
Yeah, to figure out what their other boundary conditions are. And so really, you could also think of it as like in the previous case with where lambda was negative. We plug in the boundary conditions, we get a system of equations, linear equations, and that's what pops out. Okay. But the thing is, what we find is this function satisfies the PDE no matter what lambda is. So we have a continuum of solutions, if you will. Once we impose the boundary conditions, then we have a discrete set of solutions. Because this is for n equals all positive integers. Now, before I go on, I've specified that n is a positive integer. Suppose n was a negative integer. So I just replace n with minus n. That also works. How come I don't actually need to include them, though?
Is it because of the lambda equals something squared? Is that why?
Well, I could have plugged in minus n, and lambda would have the same value.
Right.
So that's not it. Like, suppose I replace n with minus n in here. It solves the PDE, it satisfies the boundary condition, but how come it's not necessary to include it in this?
Because sign is, or it's -1, isn't it the same thing if it's 1? Because it's a sign. No, go ahead.
Were you saying something?
I started to, but I don't think it's right.
Well, go ahead, fire
I was
away.
gonna say something about absolute value of the numbers. But
Oh,
no.
not quite. Anyone else?
Well,
What do we know about sine?
Well, that's what I'm saying. If sign of -1, if it's -1, it's gonna be the
It's
same.
not,
thing.
it's a,
Yeah.
Sign of negative
Odd
pi
function?
will also
oh
be
crap,
zero.
I was gonna say odd function.
Is that what you're talking about?
Yeah.
Okay, I wasn't sure, but
Oh,
yeah.
sorry.
Okay.
Okay.
You said
What
whatever
I was
you know
saying
about
is
sign, I
making
was gonna say
sense
it's
to
an odd
me.
function.
Like, sine was negative pi, sine of negative 2 pi is also 0.
That's
But that's
Yeah,
because
that's
it's an odd function is
Yeah.
what
What
he's
he said.
getting at.
Okay. All right. Yeah. So the thing is,
I take credit where that's
yeah, fine.
You get your help. Okay. It's fine.
Okay. Yeah. So what do you get? The point is, yeah. So in the case of n, the negative integers is those are not linearly independent solutions because all they are the negatives of the solutions we already have. So in other words, yes, it gives us solutions. It doesn't give us new solutions. So the case of a positive integers covers all we actually need. Okay, does that make sense?
Are the ends the same, or does it really matter? Like the x sub n and the n of the sign, are those the same?
Oh, like this and that?
Right.
Yes.
Okay.
Yeah, so it's convenient because, we we specify boundary conditions if we have integer multiples of pi, and yes, that was already happening to a number of solutions this way. So it's like, oh, okay, I have an integer index on hand, so I'll just use it.
So any solution, it's a linearly, it's a linear combination. It's just -1 times
Right.
that, so it doesn't.
Yes, so these, where positive integers, give us a set of infinitely many linearly independent solutions. And just the positive integers is enough. Thanks. Okay.
God, I wish I knew your sound was on.
What?
I wish I had known your sound was on.
Why?
Oh wait, your sound's not on your phone.
Yeah,
Oh dang.
I'm on to
Sent
you.
the minion screaming.
Oh, God. Okay. So now to our t equation. So Tn prime plus k lambda Tn is 0. And we know what lambda is. We know what lambda is positive. So what that gives us is t sub n of t it's going to be an exponential. So it's going to be e to the minus k lambda t times a constant, but for convenience we'll just set the constant equal to 1 because we're going to be multiplying this by constants anyway. Now, I can fill in what lambda is, so it's k n pi over L squared t. Okay, so now I can, so that was easy, so now I can write down my entire solution, at least the form of it. So I have Bn, and then I have some constant, and then I have this exponential times my eigenfunction. Okay. And this is my u sub n of x and t. And we now know that this function here, each one of these for each n, satisfies both the PD and the boundary conditions. The only thing left to deal with are the initial conditions. Okay. Now, found a mistake in my dang notes. Okay. That hopefully I won't forget to fix later. So now we apply the initial condition. So u of x0, so just plug in t equals 0. So that's easy enough to do because that just makes the exponential go away. And that must equal f of x for whatever our initial condition is. Okay. So how are we going to find these constants, these b sub n? So what we do is I'm going to multiply both sides of this equation that we need to solve by one of these eigenfunctions, these signs. So I have Bn sine n pi x over L sine m pi x over L, and then I'll multiply the right side by that too, sine m pi x over L. Okay. And then what I'll do is integrate both sides from 0 to L. Just squeeze a dx in here. Okay. What I'm actually doing is I'm taking an inner product of both sides of this equation with sine m pi x over L. Now, I can use the linearity of the integral to pull out the summation and pull out the b sub n. the same right side. Okay. Now, how does this help? It helps a lot. I won't go through all the details of integration because that's so Cal 2. It is in the notes, so due to time I'll refer you to that. But what we know is that these functions perform sine integer times pi times x over L. They are orthogonal. Very nice property to have. And what that means is the integral of any function of this form, sine n pi x over L times sine m pi x over L, where m and n are integers. That's important. Is equal to L over 2, whatever L is, in the case where m is equal to n. You get a sine squared, and you can use a half-angle formula to work out the integral. If m is not equal to n, you can use a product to sum. Okay, so I'll write down what's used so you can better understand what's in the notes. Half-angle formula in the m equals n case, and a product to sum formula in the m not equal to n case. And what you get is, delightfully, 0. So what that means is all the terms on the left side go away, except for n equal to m, in which case the integral is L over 2. So what you get, so this equation I've written down here reduces to Bm times L over 2 is equal to the integral on the right side okay. So now we have a formula for our coefficients in our, it's a Fourier sine series. That's what this is. We're a linear combination of sine functions. The Fourier sine series of f of x on the interval 0 to L. So that's what we're constructing to satisfy the initial condition. And here's how we get our coefficients. So this is actually a discrete Fourier sine transform. There is a continuous Fourier transform, that's for Cauchy problems, to define in the whole real number line. But if you're working about an interval, it's a discrete Fourier transform that you use. That's just a process of computing these coefficients. So now, the problem is the initial boundary value problem is completely solved. This is our solution with those coefficients b sub n given by this formula here. And we're done.
So when we write b sub n, we're going to just plug in n for n.
Yes. Yeah.
And you're saying by product to sum formulas in like sine A, sine B.
Yeah, that's just to work out the integral.
Right.
Yeah, I mean, it's done in the notes, but
Right, yeah.
yeah. Okay. All right. Is there any questions about this? Yeah.
Never mind.
Okay.
Never mind.
All right. Now, one thing I should point out is if you go back to our solution here, we have these exponentials with negative exponents as t increases. So these decay pretty rapidly. And the thing is, as n increases, the exponent grows, so the decay is even more rapid. So in fact, these terms, as n increases, quickly become negligible. So as t increases, we can get a good approximation of a solution using only the first term. So that would be b1 e to the minus k pi t over L, so the n equals 1 case, times sine pi x over L. So that's quite convenient. That now the thing is, as t continues to increase, even that's going to decay to 0 eventually. So 0 is the steady state solution of this particular problem because it's homogeneous. But the point is, like if you want to approximate the solution like numerically, just retaining a few terms is often sufficient. And the larger t is, the fewer terms you need. Okay. Questions? Yes.
So over here, why are we assuming that for the piecewise solution of the integral,
Yeah.
why are we assuming m equals n instead of n doesn't?
Well, the thing is, we're not, because m here can be anything,
Right.
and n is something everything. But because the integral is 0 most of the time, that means that most of the terms in the summation are gone.
Okay.
So the only thing is, so so we're not assuming this. It says once we take advantage of this, this is all that's left
Okay.
on the left side.
Okay.
Yeah. So this is the magic of orthogonality, because normally, if you have an equation like this, often you're not able to solve for these coefficients independently of one another. But because these functions are orthogonal, now you can. So it's what lets you pull problems apart into much simpler ones that you can solve simultaneously.
Why do you leave the square on the e? Like in those first two ones?
Oh, shoot. Hold on a second. That square should be there as well.
So should it be on the very bottom one that you just read?
Yes. Dang it. Well, okay, not on the t.
whoa.
What?
The K not square, is it?
No, K is outside.
Uh,
Pi over L squared, right?
okay. Yes. Oh no, gotta mess up something every day.
I somehow had that one written up there.
Oh, really? Okay. Maybe it's muscle memory from 517.
I wouldn't count on that one.
Okay. All right. Yeah. So, yeah, I think because I was kept writing it non-squared in here, and started writing it non-squared everywhere. But yeah. So, yeah. So lambda itself is squared. All right. Dang it. Oh. Found a mistake in the notes. Okay. All right, how much time? Okay, I think I have an example, and I think I have just enough. Oh, yes, I do. Good. I don't want to be behind because I don't want to have to tell Dr. Xian something different for what to cover. Okay. Okay. So, for example, we have ut minus x is 0, so k equals 1 in this case. And we're working the interval 0 to pi, so that is our L. Okay. Dirichlet boundary conditions, like we've been doing. And their initial condition is something rather nasty. So our f of x is a piecewise defined function. So it's x from 0 to pi over 2, and then pi minus x from pi over 2 to pi. So the way the initial data behaves, okay, so it goes up, pi over 2, so it's a hat function, basically. So slope 1 over here, and then slope minus 1 down to here. So, because the thing is, what we're going to find is the solutions of a heat equation are smooth. So even if the initial data is not smooth, like in this case, it's not differentiable at pi over 2, because of these decaying exponentials, the solution will smooth out immediately. Now, once we compute it, then I'll draw it for you. Okay. Now, because of the boundary conditions, we can cut directly to the last part of a problem that I did over there. So the boundary conditions tell us that our solution has this form. Some constants b sub n, sine, and we have n pi x over L, but L is pi. So we're just going to have I need the exponential part. So we have e to the minus k is 1, so I don't need to include that. And then our eigenvalues,
Just one.
no. So I'll put in the eigenvalue here, just in the general case, lambda n, sine, and I'll simplify it a little bit, n pi x over pi, because pi is the value of L in this case. And then I fill in what our eigenvalue is, n pi over L squared, but again, pi is equal to L, so we just have minus n squared t sine nx. Okay. All right, so questions about the form of the solution before we go after these constants. Okay. Now, the constants, b sub n, are given by the formula that has to go over there. So 2 over L, which is pi, integral from 0 to pi of our initial data times sine nx. So now we fill in what f of x is, and we're going to get a piecewise integral. So integral from 0 to pi over 2 x sine nx plus 2 over pi integral from pi over 2 pi minus x sine nx dx. Okay. So now it's those two integrals that we have to evaluate for each n. How would we go about evaluating those integrals? What technique would we have to use? Integration by parts, unfortunately. What?
Sorry. Just don't have good feelings with that stuff.
Okay. So to do integration by parts of this, so the polynomial part is your u, the sine nx dx is your dv, and the same thing for the other one. Let's see, how am I doing on time? Oh, actually still pretty good. Okay, so I'll carry out the integration over here, where I have some space. Okay, so what we get when we carry out the integration by parts, so I have a big 2 over pi, well, I guess there's no size for it, 2 over pi out front. So our u is x, and then our v is the integral of sine nx, but that's going to be minus cosine nx over n. So this is the uv part. And then for convenience, I'm also going to include the uv from the other integral. So this is u, and this is dv. So the dv's are the same. So I'll have plus, or minus actually, minus pi minus x cosine nx also over n. Okay, so those will be u v's. And then for a v du, I'm going to have, okay, minus the integral of v du, but this is our v. So a minus and a minus will make a plus. So we're going to have plus 1 over n, integral from 0 to pi over 2, cosine nx dx. And then from this one, we're going to have this is our u, so du is minus dx. So we're actually going to have a minus 1 over n, 0 to pi over 2 to pi, of cosine nx dx. Okay. Oh, and these expressions are evaluated in their respective limits. So 0 to pi over 2 for this one, and pi over 2 to pi for this one. Because this is a definite integral, so we have to remember to plug in the limits in both cases. Okay. Now, at least these integrals are easy to evaluate because that's why we're doing integration by parts. So the integral of cosine nx is what? Sine what?
1 over n.
1 over n sine nx. So that's going to give us 1 over n squared altogether. So, okay, so I'll go over here to finish it off. Well, that's right. Are you guys going directly to analysis at 4:45 again? Okay.
So,
All right. I'm almost done. I think I can get you guys a little gap. Okay. So to do Pn, so what we get is 2 over pi. So what we have is the first term over here. So that's minus x cosine nx over n plus sine nx over n squared, and all that's evaluated at 0 and pi over 2. So this is the integral v du part. And then everything that gets evaluated at the other point, so we have minus x, or minus pi over minus x, cosine nx over n, minus sine nx over n squared, evaluated at pi over 2 and pi. Okay, so now when we go ahead and plug in all the limits. Okay, so we have, well first, when I plug in 0 in here, this is going to give me 0 because of the x. Sine of 0 is 0. So I get nothing from plugging in 0. So only from plugging in pi over 2. So I have minus pi over 2 cosine n pi over 2 over n. And then I get plus sine n pi over 2 over n squared. And the thing is, I don't know what n is. N is any positive integer, so I can't say that anything is like 0, 1, or minus 1 yet. That'll have to come later. And then over here, when I plug in x equal to pi, again, I'm going to get absolutely nothing. There's no contribution. Only when I plug in pi over 2. So that's going to give me actually a minus for one thing. So I go ahead and plug in pi over 2, and I get minus pi over 2 cosine n pi over 2 over n minus sine n pi over 2 over n squared. Okay. And then I have all these minuses all over the place. So that's, I'll just cancel them all out and give myself pluses. So how does this simplify?
Well, cosine of anything, something, the integer values of pi over 2 becomes 0.
It turns out that's going to be moot.
Oh.
Don't think about what sine and cosine are equal to yet.
Oh.
Well,
Well,
you
there's
can
a-
cancel out
yeah,
that cosine guy.
Yeah, cosines
Yeah.
cancel out anyway, no matter what that is.
Oh.
And then you get
And so
just,
it's 4 over pi.
Yeah, the sine terms
Oh.
add together. So yeah, those combined, we get 4 over n pi squared sine n pi over 2. Now we need to think about what these trig functions are equal to. So what could sine n pi over 2 be equal to?
0
Or
One,
Oh.
no, negative one.
or negative 1.
Sorry.
Alright, so well, when is it equal to 0?
It's not, what's never equal
When
to zero.
they're,
Yeah,
when they're,
it can be. Yeah, it can be.
when they're even integers.
Even integers, because then we get a multiple of pi. Yeah. Okay, so when n is even, whole thing is 0. When n is odd, this could be plus or minus 1. It's actually, okay, so you have 4 over n pi squared still, and then we have minus 1.
It's one of those alternating
Pi
series
squared.
thingies. Yes, no? No, it's got weird coefficient. Never mind. Forget what I said.
Okay,
Whatever.
k plus 1, where n is equal to 2k minus 1. So that, because when k is equal to 1, n is also 1. And we get sine like pi over 2, 5 pi over 2, etc. It's equal to plus 1 in that case. And all the other times is equal to minus 1. Okay.
but
Yeah.
is it n squared pi?
Oh, dang it. Yeah. Yeah. N squared pi. I need a spring break. Okay. All right. Now, so now what I can do is fill these in, but I'm only going to have terms corresponding to odd n. So my solution will be a sum. Okay, so I have 4 over pi out front, and I'm going to make a sum over k rather than n, because at least then values of k are consecutive, and n will always be odd. So then I'll have this expression, minus 1 to the k plus 1 over n squared, but n is 2k minus 1. Okay. And then I have, oh, no, I'm mistaken a note. Exponential, so I'll have e, I had that earlier, so e to the minus n squared t. And then I have sine, so I have my solution from over there, so I'm just basing it off of that. Sine nx, but that is the same as sine 2n minus 1, 2k minus 1 x.
Do you not want to substitute on that exponential?
Yes, I can. Just to get n out of the picture altogether. Yeah. In the notes, I somehow left out the exponential factor altogether. 2k minus 1 squared t. Okay, and we're done. That's the solution. So we have these piecewise data. So the solution over time. Okay, I swear to God, it'll be done in like 3 minutes. So you have a 5-minute break. Here's our initial data as this only piecewise smooth hat function, and then over time, it smooths out and starts decaying towards 0. But this smoothing happens instantly. So if you pick any t whatsoever greater than 0, the kink is gone. So that's what happens. Diffusion of heat energy, even if the initial temperature profile has a kink or discontinuity in it, the actual temperature distribution for any positive t will immediately be smooth. So that's just how these solutions behave because of the decaying exponential. Whereas wave equation, discontinuities or kinks tend to persist.
Could you repeat that?
Solutions of a heat equation are smooth for any positive t. They smooth out immediately. solutions of a wave equation don't have these decaying exponentials, so they tend to retain discontinuities or kinks.
So that's good news.
Well, it depends on what you consider good news, but yeah. If you really want to keep those things, but maybe you want smooth solutions. So they're definitely easier to analyze. So.
For that 2D problem, will it be, or is it a different thing?
Oh well, for heat equation, you'll keep those. Yeah.
We'll keep those discontinuities
Yeah.
because you want.
Yeah. Well, your numerical solution will have a combination of not discontinuous, but non-smooth functions. Yeah.
So then this news is not very like.
Well, actually, it is helpful for numerical solution because it means you'll have to retain a few terms. Like if you want to approximate this, which is, and that's all you're doing when it's numerical, you would only keep enough terms. Like you would see, at what point is this negligible? And as t gets larger, this is decreasing rapidly to 0. So you would cut off sooner. Also, this helps because those are decreasing also. Yeah. So if you were to plot this, like the terms for a specific t, you'd find that the terms quickly grow smaller because of that decaying exponential. So yeah, so for numerical approximation, that's quite good. Whereas for wave equation, you have to retain more terms, and that becomes harder to deal with. Okay, you have a question? Oh,
If the boundary condition is not equal to 0 at both ends, so this one
okay.
is different. Right?
So if it's still Dirichlet, but it's equal to something non-zero,
Yes.
the easiest way to handle that is you come up with a linear function of x that satisfies the boundary conditions. So it could still depend on t, boundary conditions. So, and then you subtract that off. So now what you're doing is you're solving a non-homogeneous PDE with homogeneous boundary conditions and a modified initial condition. Now, we haven't talked about non-homogeneous PDE yet, but that's actually easier to handle. Because we would get an extra term in the solution.
So we do not follow these steps.
Well, you do to a point, because basically what you're doing is you're solving, it's called Duhamel's principle. I'm going to regret writing this purple chalk, but it's what was there. Provides a natural way to express a solution to a non-homogeneous PDE in terms of homogeneous solutions. Basically, it's an integral of a homogeneous solution. It's like when you're solving non-homogeneous ODE and you do like an integrating factor and that sort of thing. It's like that, actually. And I haven't looked ahead in the book, but I believe we cover those later. So we'll see more of this, but that's the idea. So there is a procedure for handling non-homogeneous boundary conditions.
Okay, thanks.
Okay, so I guess half you can go to analysis. And okay, I gave you 3 minutes. I tried.